Hello, my name is Augusto Jang, and this is my presentation for Lab 2. So in this video, I'll be talking about projectile motion and my computational models for the projectile motion lab. So the main concepts behind this are projectile motion, which is a motion of an object that is launched into the air and is acted on by two main forces, which is gravity, which pulls the object downwards with acceleration of 9.8 meters per second, and drag, or also called air resistance, which always points opposite to the velocity of the objects. And the velocity and is proportional to the square of the object speed. And without air resistance, the only force would be gravity, so the trajectory would basically be a parabola. And with air resistance, this path would become shorter because drag would remove energy from the system. So to test this, I threw a crumpled paper ball into a trash can and recorded its motion. And then I analyzed the video using Tracker by finding its points to create a position versus time graph. And I did this frame by frame. And this gave me data that I could compare to create a model against my code. Okay, when I made the code, I had to create a few variables, as you can see, and put it into the while loop. So f of g is basically just the force of gravity in the negative y direction, which is negative mass times gravity. And Fd would be the drag force, which equals negative b of v squared times v hat. B would be the drag constant that I could choose for the experiment, and v would be the velocity magnitude, and v hat would be the unit vector of velocity. And ball dot velocity is just the velocity vector of the object, which is updated by using the while loop, using the net force that I made in the equation. And the net force obviously would be F net equals Fg plus Fd. And using Newton's second law, the code updates the ball's velocity and position. So when I compared my computational results with the actual results, considering drag with gravity and just gravity, I found a strong correlation between the two, or the three. The overall shape matched really well. But one interesting observation was that when I simulated the drag in my code, the x distance that the object traveled decreased, which makes sense, but the y position increased within the same time frame. And this did show that drag changes motion, but it also highlights that my initial velocity measurements, or maybe the shape of the paper ball and its effects with the air, could have not been perfectly illustrated with my experiment. And moving on to the discussion about terminal velocity. So in theory, an object would experience terminal velocity when drag would balance out gravity. So the net force would be zero. And because my experiment is really short, I didn't really see a terminal velocity. And to do this, I would maybe throw the ball from higher chair, not even a chair, maybe like a stairwell or something, and track the velocity over time until it becomes constant or levels off. And for the what if question, if the paper ball was thrown straight up with the same initial speed, I think the total flight time would be longer because the object would go up a certain height, stop, and then fall back down. And then the added distance makes the flight time of the object in the air longer, even though drag would still reduce peak height. So in conclusion, adding drag to the model changes the distance traveled. That normally reduces both horizontal and vertical displacement, but in my data, the x distance decreased, and my y distance increased, likely due to aerodynamics of the paper ball, like I said before, or small errors in measuring the initial velocity. And for future improvements, we considered filming in a fixed place like a tripod, or making sure the balls swim away from the same height always. We were calibrating a tracker to the exact known scales. Thank you.